In this video, we're going to cover the code for the pre-processing step in our nonlinear p-delta analysis solver, and this code is reused in any other solver that you develop. And we're going to refer to this code using an example being our simple frame that's fixed at the base and subjected to a gravity load in the middle of the beam and a wind load at this corner node of the column, or lateral load. So the parameters we take into this function are the length and height of the frame, the number of subdivisions of elements along the length of the beam and along the height of the column, the gravity load, wind load, number of iterations for our p-delta step, and the convergence tolerance. So I'll go through the more important parts of the code in more detail. So the first step is straightforward, where you compute the number of nodes of the structure and a number of elements. And then the next part, we have structures to store the data for the nodes and elements, being the x and y coordinates, the translational and rotational restraints, and the displacements and rotations in local and global coordinates. And each element points to two node indices, a material ID and a section ID, and it has a connectivity array to connect the local stiffness matrix to the global stiffness matrix of the structure, and each element has a length, a stiffness matrix, displacement vector and force vector for the elastic analysis in local coordinates, a geometric and tangent stiffness matrix, and displacement and force vector for the p-delta analysis in local coordinates, and we have a transformation matrix from local to global coordinates, and we have the transformed stiffness matrix, displacement vector and force vector in global or transformed coordinates. So we don't need to store all this data, but it's good for debugging the solver and visualizing the results. And next we have a structure to store the section data. So we have the name of the section, the type, the cross-sectional area, and the second moments of area, about the major and minor axes. So for example here we have a beam column with the following section properties, and a beam with a very large axial stiffness, because we model the beam as being restrained by a slab in a high-rise building. And here we have a structure to store the material data. So for example, here we have steel, and it's an elastic material with the following density and a Young's modulus and Poisson's ratio. So here we only use the Young's modulus because we're modeling beams and columns in a static analysis. And you can add as many sections and materials as you like, depending on your problem. And next we subdivide the structure into nodes. So in our example structure, we want to divide the beam and column into two elements each, and this code divides a structure column by column and then divides the beam. So we have node 1, node 2, node 3, node 4, and node 5, node 6, node 7. So note that this code has logic, so the corner nodes don't overlap. So if we run this code at this stage, so we subdivide the beam and column into two elements each, our nodes look something like this. And next we create the node sets. So this node set points at the fixed node indices being 1 and 2, and then the next node sets are for the left and right column. So for column 1, the node indices will be 1, 3 and 5, and for column 2, 2, 4 and 7. And the indices of the beam nodes are 5, 6 and 7. So effectively, these are arrays that store the indices of each node. So for the beam, we have 5, 6 and 7 as the node indices in this array. And we have a node set for the gravity load and wind load. So this node set will store node index 6 to apply the gravity load, and the wind load node set stores the index of node 5. And then the next bit of code subdivides the structure into elements. So we divide column by column first. So we have element 1, 2, 3, 4, and then the beam elements are 5 and 6. So that's what this code does. So if we output the results at this step, by stepping through the code, we see our elements for the frame. And then next we create the element sets for the left column, right column, and beam. So for the left column, our element set stores element indices 1 and 2. And for the right column, elements 3 and 4. And for the beam, elements 5 and 6. And next we impose our boundary conditions. So recall our fixed node set, pointed to nodes 1 and 2. So if we go through this node set, we get our node index from this set, and then we take the node at this index and set the translational and rotational restraints to 1, meaning active. So in other words, node 1 and 2 are both fixed. And next we construct our ID matrix. So this matrix is going to be used to set the restraints, set the loads acting on a structure. It's going to be used to assemble the element stiffness matrices into the global stiffness matrix of the structure and extract the results. So this is a very important matrix. So in this matrix, the columns represent each node. So we have node 1, 2, 3, 4, 5, 6, and 7. And the rows represent the degrees of freedom. So we have translation in the x direction, in the y direction, and rotation about the z-axis in the third row. So initially, we set the restraints of our base nodes to 1, meaning that they're restrained, and the other nodes are released, so we set the degrees of freedom to 0. And in the next step, we go through this ID matrix column by column and replace the ones with zeros. So we have 0, 0, 0 for nodes 1 and 2, and then increment the release degrees of freedom in the remaining columns. So what we have is 1, 2, and 3 for node 3. So the node can move in the x and y directions and rotate about the z-axis. And for node 4, we have degrees of freedom 4, 5, and 6. So we just keep incrementing the numbers. And node 5 is 7, 8, 9. And the degrees of freedom of node 6 are 10, 11, and 12. And node 7, 13, 14, and 15. So essentially our structure has 15 active degrees of freedom. And we'll see how this ID matrix works in an example where we assemble the load vector in the linear elastic analysis step. So essentially, given our structure has 15 degrees of freedom, the load vector is going to be a 15 by 1 vector. So remember that we had our node set for the gravity load pointing to index 6. So we're going to apply the load at node 6. So we extract degree of freedom 2 and node 6 from the ID array. So we have row 2 corresponding to the y degree of freedom, and column 6 corresponding to the node. So we apply the load at degree of freedom 11. So our load vector is so far 0, 0, 0, corresponding to 1, 2, and 3, and 0, 0, 0, corresponding to 4, 5, and 6, and corresponding to 7, 8, and 9, it's still 0. And let's continue this here, because I'm running out of space. So at degree of freedom 11, we're applying the load. So we have 0 for degree of freedom 10, the gravity load at 11, and 0 at 12. And at 13, 14, and 15, we have no loads, so the load vector is going to be of zeros. So note that we initialize this vector to zeros initially, and then we apply the gravity load. And then next we apply the wind load. So the node set of the wind load points to node index 5. And we're going to apply the wind load at degree of freedom 1 and node 5. So we have row 1, column 5, corresponding to degree of freedom 7. So we have 1, 2, 3, 4, 5, 6, and 7. And that's where we apply the wind load. That's what our load vector for the structure in our linear elastic analysis in transformed or global coordinates looks like. And in the next step, we assemble the connectivity arrays for each element. So effectively, each element points to 2 node indices, and each node index has 3 degrees of freedom. So our connectivity array for the element is going to have 6 entries in it. And this is going to be used to link the local degrees of freedom of the element to the degrees of freedom of the structure. So in other words, for each element, we have the local degrees of freedom being 1, 2, and 3, 4, 5, and 6, corresponding to the translations and rotations at node 1 and node 2. So for element 1, we have 3 inactive degrees of freedom at the first node, and the next node points to degree of freedom 1, 2, and 3 in the structure. And another example is the connectivity array of element 4. So that connects the local degrees of freedom, being 1, 2, and 3 at node 4, and 4, 5, and 6 at node 7, to the degrees of freedom of the structure. So the connectivity array for element 4 is 4, 5, 6, 13, 14, and 15. And this is going to be useful in assembling the stiffness matrix of each element to the global stiffness matrix of the structure. So given that each element has 6 degrees of freedom, it's going to have a 6 by 6 stiffness matrix, and the structure has 15 degrees of freedom, so the stiffness matrix of the structure is going to be a 15 by 15 matrix.